In this video, we want to expand on some of the earlier thoughts regarding welfare measures, and we want to start with index numbers. Index numbers are welfare measures to some extent. Now, you're familiar with one particular index number, and that's the Consumer Price Index, or CPI. But here we're talking about quantity indexes. So we look first at the Laspeyres quantity index, and it's given by Q of L is equal to the sum of the quantities multiplied by their prices in the original situation. So here we have the original situation and the original prices, which are given by this line with one arrow on it. And we use those prices to weight the quantities in the future bundle or future situation. So we have the sum of the original prices times the future quantities divided by the sum of the original prices times the original quantities. So the Laspeyres quantity index is given by the sum of the prices in the original situation times the quantities in the future situation divided by the prices in the original times the quantity in the original. And we actually create the quantity index by subtracting from the numerator the denominator. This is the denominator and the numerator, and then we get that the Laspeyres quantity index is simply prices at the original situation multiplied by the change in the quantities. Now we have an alternative index, which is the Pasch quantity index, which is very similar, except now everything is in terms of the prices in the future situation, 1. So it's given by the ratio of the sum of the prices in the future times quantity in the future divided by the future prices times the current quantities. Now, one of the problems with this index, of course, is that we might not know what the quantities are in the future. So a CPI, for example, will weight the quantities by the original prices because those are available. All right, so L is a index similar to the Consumer Price Index. So the Pasch Index, if we take the numerator and subtract from it the denominator, we get the sum of the prices in the future situation times the quantities in the future situation minus the sum of the prices in the future times the current quantities. And then we can rewrite that as the sum of the future prices times the change in the quantities. And these two quantity indexes, L, Laspeyres, and P, Pasch, are in level form. Now, if we take a Taylor series expansion of the expenditure function about the final situation, so about this situation here, and you'll see that in this situation we have the future prices given by this line here, and this is the current prices. So we're looking at the future quantities and prices at 1. So what we want to do is you want to take a Taylor series expansion of the expenditure function about the final situation. So the expenditure function at original prices and future utility, which is this one here, which isn't labeled, this is U0 and U1 and U0. And what we want to do is we want to take the Taylor series expansion about the future price. So about this future price as opposed to the original one. So it's given by the expenditure function at the future price and the future utility minus the sum of it turns out that these are the compensated demands of the future price and future level of utility times the change in the prices plus some remaining term which refers to the third and fourth derivatives, the Taylor series expansion of. Now, this compensated demand function is derived from Shepard's lemma, which says that the partial of the expenditure function of P1U1 with respect to PI is given by QIC. But now it's very important to recognize that because the and we showed that in the earlier video, and we'll show it again below. But at the point where the ordinary and compensated demand functions intersect, this QIC and QI, the ordinary demand function, are pretty well substitutable at that particular point. So if we look at this, we find that the equivalent variation here is given by the minus of the quantity, the demand at that point, 1 in the above diagram, times the change in price of I, plus the change in income given by delta M, plus this remainder term of the higher order Taylor series expansion. So we add and subtract this term here, which is equal to PIQI1. And when we do that here, we get this result that the change in income is given by the quantities in the future situation times the changes in price plus the changes in price, or the price in the current situation times the changes in quantity. This star refers to the proof which we'll give below. Substitute that delta M into this expression here for EV. Okay, so we're going to substitute this value of delta M into this expression here, and then we're going to clean it up, and we find that the equivalent variation is simply the sum of the original prices times the change in quantity plus this remaining term, which we assume will go to 0. Laspierre's quantity index in level form, L, is a first-order Taylor series expansion of the equivalent variation. So we can prove that. So let's go to this proof. So we're going to try and prove, where is that? Here, this star. All right, so we're going to add and subtract this term. All right, so here we have delta M is given by the prices times the quantities in the future situation minus the prices times the quantity in the current situation, the sums of those. And now we're going to add and subtract this particular term. Here, we're going to add that and we're going to subtract it again. So we have this expression, which is given here, the first two terms. We're going to add and then subtract that same term here. When we do that and regroup, then we get that the sum of the difference in the prices between the future and the current situation multiplied by the appropriate quantities in the future situation plus the change in the quantities from the future between the future situation and the current situation multiplied by the price of the current situation. Then we get the sum of the QIs at the future times the change in price plus the sum of the prices in the current situation times the change in quantity. Then from earlier we found that EV was the sum of QI in the future situation times the change in price plus that delta M, and we substitute in the delta M and we get this expression here, including this remainder. And when we clean that up, we find that EV is simply given by the sum of the current prices times the change in the quantities for each I. And that's our Laspierre's index. So the Laspierre's index is a Taylor series approximation of the equivalent variation. Okay, let's look at this diagram here. What we have here is, again, a current situation and a future situation denoted by 0 and 1. The current price is given by, the current price is this one, P0, all right, and M0 is the current budget. Now over here we have Q1 on the horizontal axes and all other commodities on the other axes. Now if Qn is a required quantity, something that we require, and Q1 is not, then we would expect these indifference curves to intersect this vertical axis. M0 is equal to E P0, P0, U0. That's what M0 is, and the same thing with M1 is E P1, U1. So we can look at this here, which is the expenditure function of P1 given U0, and this is our new P1. These are our new price ratios. So we find that the price ratio for M1, so what we've done is we've reduced the amount of income available to this person. The price has changed as well. It's gotten less expensive to purchase Q1, so the price of Q1 has gone down, and this is denoted by this P1. P0 is the original price. If we retained or wanted to stay on this utility function U0, we'd move to point A. So 0 to A is our substitution effect, but then because we have that new income, that brings us out here. So from A to 1 is our income effect, and we then shift from here to there. And we calculate the compensating variation as M1 minus E P1 U0. This is our compensating variation, and we can rewrite that as M0 because what we're doing is we're adding M0 and subtracting M0. We subtract M0, we add it here, and we get minus E, the expenditure function P1 U0, plus M1 minus M0, which is the change in M. And we get, when we substitute this M0 for M0 here, we get the expenditure function at P0 U0 minus the expenditure function at P1 and U0 plus the change in income. So basically what we're doing is we're saying we're going to go from 0 to A, which is this part, and then from A to 1, which is given by delta M. Now we also have the equivalent variation. The equivalent variation says that we look at the current prices, and we look at the future utility, and we subtract from it M0. And again, we do the same thing. We, in this case, subtract M1 and add M1 back, and this gives us, when we sort it out, this thing here, because M1 is simply the expenditure function P1 U1. So this is our equivalent variation measure. Now we also have something called the Bergson-Samuelson social welfare function, or SWF. And here, I'm sorry, I went from Q1 to X1s. I'm using X's here. Partly this won't confuse you a bit, but the Bergson-Samuelson social welfare function is W is a function of the utilities of individual people who purchase X1 to Xn, and we assume that there's M people, and we can then write this function as a function of X1 to Xn. Now, we assume strong separability. That's an assumption that we often make, and that means that the social welfare function, and this really is the Bergson-Samuelson social welfare function, is that it's a function of the utility quantities of all the individuals summed up. If we assume strong separability, then the social welfare simply equals the sum of the individual utility units. Further, we cannot judge one person to count more than another, so the utility weights are all equal. Okay, the utility weights are equal. There's a 1 in front of these, and everyone counts the same. How do we make any other decision? We can't, because that would involve some kind of a value judgment. Then we have that utility of any person is given by a function of X1 to Xn, and we can write that as the utility of income. So utility is a function of income. So think of substituting the Marshallian demands into the utility function to get that indirect utility function, which we denote as psi as a function of prices and M. Since all agents face the same prices, income is what differs between people. So that's one reason that we're able to do this here. So recall that lambda, the Lagrange multiplier, turned out to be the marginal utility of income, or we write it as marginal utility of M, which is our income, or the first derivative of the utility function with respect to M. These likely differ from one person to the next, because U prime M is greater than 0, so utility as a function of income is always positive, and it increases but at a decreasing rate, which is that. But determining the marginal utility of income for individuals and for different levels of income is a judgment call. So what's often assumed is that the marginal utility of income is constant, and not just constant for an individual, but that the same marginal utility of income applies to all people. In that case, the social welfare is then the sum of people's incomes, and it's summarized as GDP, if you like, with some modifications often for non-market values. And as a result, the change in welfare that we get is simply any change in GDP. But GDP needs to be measured in terms of actual welfare benefits and costs. But these kind of assumptions underlie cost-benefit analysis. All right, let's turn back to our diagram here, but now in terms of X1 and X2 instead of Q1 and Qn. So going from bundle 0 to bundle 1, if the actual prices in situation 1 are used as reference prices, the welfare changes measure compensating variation. So if future prices are used as the reference prices, we get compensating variation. If the original prices are used in situation 1, then the welfare change measures equivalent variation, or EV. A useful application of the expenditure function is that for a select set of reference prices given by P superscript R, the expenditure function for those prices and for a given utility represents the minimum expenditure needed to attain indifference curve U. So whatever indifference curve we choose up here, if we're given reference prices, then the expenditure function with those reference prices represents the minimum expenditure needed to attain that indifference curve U. So we substitute the indirect utility function into the expenditure function to get the equivalent income function, which is then the expenditure function as a function of these reference prices, any other prices, and income, and that's equal to the expenditure function at the reference prices with then the indirect utility function put in there, and that's equal to the sum of the prices times the reference, or the reference prices times the individual XIs, where XIs here are your compensated demands, but remember they intersect, as we will see below, at the point that we're doing the evaluation. So we have the compensated demand functions as a function of the reference prices and the indirect utility function. The equivalent income function allows us to find the level of income needed at some vector of reference prices for the household to attain the same utility level it enjoys from income M and prices P. This measure is referred to as a money metric utility and is used to measure household welfare in a meaningful way. If preferences are quasi-homothetic, the expenditure function can be written as E function of A, where A is a function of prices, plus utility times this B as a function of prices. And because we have an A and a B here, we have a linear homogeneous expenditure function. And U is quasi-linear homogeneous. For quasi-homothetic preferences then, the uncompensated demand functions are given by Xi equals AI at prices P, Bi at prices P divided by B as a function of P, M minus A with respect to P. How did we get that? Well, I'll leave that to you, but we use Shepard's lemma to find this Xi based on this particular expenditure function. We just have to make sure that we put the i's in the right spots in that expenditure function for a particular good xi. Now, recall the Slutsky equation from the earlier videos. So we write the Slutsky equation as the partial of xi with respect to pj is equal to the partial of the compensated xi's with respect to pj minus xj compensated. So these are compensated demands, partial of xi with respect to m. Recall that this compensated component here, where we take the partial of the compensated demand function with respect to pj, we write as s sub ij minus this xj compensated times the partial of the demand function with respect to income. Now, we can then reorganize this so the Sij is equal to dxi dpj plus xj dxi over dm. Notice that observable from the ordinary demand at point where an uncompensated and compensated demands intersect. So what this is saying is that this is the substitution effect, and we can observe that substitution effect through these equations. We can actually estimate it, but what we do is we assume that at the point where the Hicksian and Marshallian demand functions intersect, that's where we find this xj. So in other words, we can substitute this xjc for the xj, the compensated demand, we can substitute for it by taking the actual uncompensated or ordinary demands, and we can calculate what those are at a particular price. So we can rewrite this Sij as the second partial of the expenditure function with respect to pi and with respect to pj, which is equal to the partial of the compensated, because we're at that intersection point of the estimated demand function with respect to pj. And then we can use that information to get the compensating variation as being equal to this expression here. So that expression, this expression here, is observable. Everything in it, everything to the right, is observable, and as a result, we can actually calculate what that is. We can actually go out and calculate this and thereby determine the value of compensating variation. Now, one wrench that gets thrown in here is wonder if we have a quantity restriction. Wonder if the government imposes some kind of a quantity restriction. So suppose that x1 is restricted at x1 bar, and a household must consume some amount of x bar. This causes consumption at Q on the utility curve U0. So we end up at Q, we're forced to Q on U0 rather than A at U1. So what we have here is a price line that stops here but actually continues as a dotted line down here, and we would go to A if we had the opportunity to purchase beyond X1 bar. Okay, but we can't do that. We're restricted to X bar, so that forces us to be at that point Q, and at Q we get a price ratio P1 star over P2 instead of the original P1 over P2. So the effective price ratio is P1 star over P2 rather than P1 over P2, and the constrained expenditure function then has to include this X1 bar in it, along with prices and utilities. So that expenditure function is equal to P1 X1 bar plus the minimum of the X2 to Xn of the prices times these Xi's, where I is greater than 1. and that's subject to, we want to maximize that, or pardon me, we want to maximize that subject to this constraint. And that constraint tells us that we are at point Q on U0. So we can take the partial of the expenditure function with respect to any PI, and we get that all of these compensated demand functions for any I not equal to 1 are a function of prices and utility and the quantity constraint. Other than the quantity constraint Q1 bar entering the demand functions, the constrained compensated demand functions have the same properties, namely negativity and symmetry, as the unconstrained ones. So if we take the partial of this expenditure function with respect to the x1 bar, we find that the partial of E with respect to U times the partial of U with respect to x1 bar is equal to P1 minus P1 star, where P1 star is the shadow price of the rationed good. Now recall that the partial of E with respect to U is equal to the partial of M over U, which we write here as partial of U with respect to M, is equal to 1 over lambda, where lambda is that shadow price. So du, partial of du with respect to x1 bar is equal to lambda P1 star. The partial of U with respect to xi is equal to lambda times pi for all I not equal to 1. And then if we look at the ratio of du dx1 over du dx2, we get P1 star over P2, which is the result that we had on this red line here. P1 star is the price that, if x1 is not rationed and the household is free to choose, they would choose x1 bar given just enough income to attain U0 in the above figure. So P1 star would be chosen if there was enough income, just sufficient to get to U0. A problem in economics is to find shadow prices. Here, what we're looking at is a case where G is all market goods and Q is some public good. You can think of Q as being minke whales in the ocean or grizzly bears or something like that. And now what we do is we've got our income constraint here is just a horizontal line. We also note that these indifference curves have to intersect the vertical axes at 0 because you must have some amount of good G, amount you need to live. You need to live, so you have to spend some amount of money on G. And with a budget constraint of M, given that you have Q0 amount of the public good, Q0 amount of grizzly bears, let's say, then you would end up being right here on U0. And this assumes, of course, that you have an increasing utility in this direction as Q increases. So now you're going to be faced with a proposed change to go to Q1. And the question you have to ask is, what do I have a right to? Do I have a right to this U1 to Q1, or do I have a right to Q0? If the answer is you have only the right to Q0, then what happens is we want to know how much you're willing to pay to go to Q1. And the maximum amount you're willing to pay is given by this CS, which is the compensating surplus, which is much like the compensating variation we had seen earlier, but here we don't have budget lines. We don't have these budget lines that are downward sloping. We have a vertical one. If you have the right, on the other hand, to this point, to Q1, then the question is, how much would we need to compensate you to stay at Q0? And the answer is the equivalent surplus, ES, which is this difference. So in calculating the compensating variation, or which is, the compensating surplus, we ask the question, well, how much are you willing to pay to get to Q1? And the answer is, I'm here to begin with. I want to go to here. This is the gain that I make. This would be my compensating surplus. And it's equivalent to compensating variation, which says we're at this point now, but now we're changing the price. We're lowering the price of Q, let's say. And in this case, we'd have budget lines, and then the question would be, how much would you be willing to pay for the lower price? And likewise, that equivalent surplus assumes that you have a right to the new indifference curve, and you have to be compensated so that you stay at U1 but at the old Q0. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.